Look at section 3.2. Expand the screen. And the explanation in this section is really not terribly long, but we're going to get into some graphical stuff here, which is going to be a little different for you, but hopefully I can explain it to you easy enough and clarify it. We may or may not get through this whole section, but we'll get a good start. So section 3.2, which is titled The Derivative of a Function. And I have given a handout to the students here in the classroom, which I'll scan and post along with this recording. So if you're watching the recording, then you can always print this out as a reference, which we'll get into probably about halfway through this lecture. Now, there are some different notations when we talk about the first derivative of a function, which is also the slope of the tangent line. We've already discussed this f prime of x being the notation representing the limit as h approaches 0 of the difference function, the difference quotient, which is the slope of our tangent line. But what we're going to note, there are other ways of writing this, and they get into great detail of these various notations in this section. And there are a few of them we definitely use, but just kind of so you can see what it looks like. And they do get pretty wild in their notations. The first derivative of x can also be written as y prime. We do this quite frequently. Just write it as y prime, which is also written as dy dx, which could also be written d of f dx. Now, I don't usually do that. I've seen it before. I don't usually do that. Which can also be written as d dx of f of x. You can see there's many ways of writing this. And then the ones I really have so seldom seen are these versions. I don't know that I have ever seen this, but it's been a long time since I've been in differentials calculus, so maybe that's where it's coming from. And I have seen this one, d base x of f of x. Okay, so here's a bunch of versions. These first three I will do very frequently. You will see this a little more written in your calculus book at this level, and this you might not see for many, many years, if ever, kind of thing. So there's some weird notations, and they throw them around in the textbook just to try to get you exposed to them, I guess, or comfortable with them. But you will see me run through these first three most frequently. Okay, another thing is when we evaluate the first derivative at a number, you can put it like this. You know, so suppose we said evaluate f prime at x where x is 2. That's how we would write it. Now, another way of writing this would be to say dy dx as x equals 2. And you've already seen me write this when we've been finding the slope of the tangent line with that vertical line and giving a value of it at the bottom. So you're going to see more and more of this in your textbook with this vertical line at the bottom showing what number you're substituting in for x. We don't usually do the y prime version of this. I'm not certain why, but that's not natural. But here's another version of it. Okay, so you're going to see this notation also. So just kind of getting comfortable with the different ways they can present their questions to you and not letting the notation kind of throw you off track. Here's an example of how they're going to ask you such questions. They might say, let f of x equal the square root of x. And then they'll say, find f prime at, say, 3. Now, fortunately, we've already done this in the last section, but really what you would end up doing to answer this question is to find f prime of x, you're going to have to evaluate the limit as h is approaching 0 of the difference quotient, which we know takes a whole page of algebra. Takes a lot of work. But I've already done this for you. I think we already did this. And this turns out to equal 1 over 2 square root of x. In fact, we just did that just a few minutes ago when we were talking about section 3.1. So therefore, if they ask me what is the first derivative value at 3, where the x value is 3, you take this result, 1 over 2 square root of x, and now it's 1 over 2 square root of 3. And I have seen some inconsistency inside the software package as to whether to leave the radical in the denominator of the fraction or not. Sometimes they tend to leave the answer like this, and sometimes they tend to do what they call rationalize the denominator, which is something you're probably most familiar with from trigonometry. But you know, from trig, you were never supposed to leave a radical in the denominator of a fraction, and the way we got rid of it was to multiply times the radical over itself, and then the result was the square root of 3 over 2 times 3, which was the square root of 3 over 6. So this could be rewritten as the square root of 3 over 6. So kind of be aware, this doesn't seem to be very consistent yet in my math lab, but either answer at this point is correct. So you can see that is not difficult to do. Now another question similar to this is they'll say let y equals, say, 1 minus 1 over x. And then the question will be, find, and they might ask the question in this format, find dy dx when x equals the square root of 3. That's how they will write the question, which means go through the whole limit process and get that result, and then plug in an x value of negative 3. So dy dx, or in this case, when you find y prime, or dy dx, this is when you're going to go through that very lengthy process of evaluating the limit of the difference quotient, okay, which we know is very time consuming. We've already done this. And I believe this was an example directly from what we did in the last section in our notes, and the result turned out to be 1 over x squared. So that's a whole page of work that I just written in this one little equal sign right there. One whole page of algebraic effort between here and here that we've already done. And so then when they say evaluate dy dx when x equals the square root of 3, that means plug it into this square root of 3 squared, which makes it 1/3. Which in the end is the slope of the tangent line to this original curve when the x value is the square root of 3. You'll just kind of get to where you go through the algebra because of all the notation, but underneath it all, that is what you're coming up with. Now another interesting thing in this section, and I'm not going to push it very hard, but I'm going to show you one example of it because they really do discuss it at length. Is another version of the difference quotient, or another version of us finding the slope of the tangent line. So I'm going to show this to you and work a full example. So it's an alternate formula for the derivative. I'm not going to overemphasize this, but I do need to show you one example to make you comfortable with it. You may or may not ever do it again. Okay, we have defined from the last section that the first derivative is found by taking the limit as h is approaching 0 of f of x plus h minus f of x over h. And you're going to get really good at writing this over and over again. And they come up with this new version in the textbook where it might be sort of easier to do it algebraically, where they replace x plus h with a new variable z. Okay, they replace the x plus h with a new variable z. Now, the only x plus h you're seeing in our difference quotient is as the function value. But reality is that really this difference quotient, that denominator was defined, and you'd have to really go back to earlier in the semester. This h was really, what was it? It was x plus h minus x. Okay, the x plus h minus, which gave you the difference of the horizontal distance between the 2 points of the secant line as h. And so that's really how it looked, and we reduced it to h. So if you replace all these x plus h's with a z, this limit becomes the limit as the limit of what? F of z minus f of x over z minus x. And the limit is now not as h approaches 0 because you don't have h in here anymore. The limit now is defined as z approaches x. Okay, you don't even have h in this quotient anymore. And so all of this is explained a little more at length in our textbook on page 107. Here it is in blue. And they talk right up here. We write z equals x plus h, and then they show this new version or the alternate formula of the derivative. So we can do one of these examples very quickly, and take it or leave it kind of thing is my opinion, but I need to at least show it to you. So here is an example. Suppose they ask me to evaluate dy dx as x equals the square root of 3. This is really identical to the last example, but we're going to use this z version. Okay, we're going to put a z into this instead of the x plus h stuff. We're going to use a z. So in order to make this happen, this alternate version of the difference quotient is going to be the limit as z approaches x of f of z minus f of x over z minus x. Well, here's the curve. So I'm going to put it kind of in function notation. Instead of claiming it as y, I'm going to claim it as f of x so that it flows more smoothly in with this difference quotient. So if f of x is 1 minus 1 over x, then f of z, which is now part of the difference quotient, f of z is simply 1 minus 1 over z. So when I plug these versions in to this difference quotient, this alternate version, f of z is 1 minus 1 over z. My z's are kind of funny looking. Minus f of x, which is 1 minus 1 over x, all over z minus x. So now you have to clean this mess up, because this is a very large complex fraction. So this is going to be 1 minus 1 over z minus 1 plus 1 over x. So the 1 minus 1 makes no 1 anymore, makes a 0. So this becomes the limit as z is approaching x now of a negative 1 over z plus a 1 over x. Now, to put these two fractions together, I'm going to have a common denominator of zx. So this becomes the limit as z is approaching x. The new denominator is zx in the complex fraction, the numerator of the complex fraction, which is going to make this a negative x plus z with that new denominator of zx on both of those. I don't find this to be a whole lot easier, but whatever. We will go through the processing. So this becomes a negative x plus z over zx all over z minus x. Well, a negative x plus z is the same thing as z minus x, right? So this is really z minus x over zx over z minus x. So now if I multiply this times 1 over z minus x and the numerator times 1 over z minus x, then finally I get the limit as z is approaching x of just 1 over zx. Over 1. And then when you have z approaching x, that means substitute an x value in place of the z when you evaluate this. So this becomes 1 over x times x, which is 1 over x squared, which is the slope of the tangent line at any point along that curve. So I don't know that it's any easier, really. It's just an alternate way. So this is the slope of the tangent line, which is also referred to as dy dx, which is also referred to as y prime. So now when they ask the ultimate question, which is what is dy dx at an x value of the square root of 3, this is 1 over the square root of 3 squared, which is 1/3, which means the slope of the tangent line to the curve at the point square root of 3 is 1/3. So it's interesting. You can see I'm not terribly sold on it. Do what? I'm sorry, one more time? Do you have to show all this work? Yes. I could see several places where you could skip a step. So instead of having like 6 or 7 steps, you would have 4 or 5, something like that. Okay. I know. Even I hear my voice getting kind of monotone as I'm teaching this. It's like, oh, here we go again. Okay. So here's where it's getting ready to get interesting. And I have to be really careful even with this information. I try to keep it clean for you. Okay, graphing the derivative. Graphing the derivative. Now this is a little bit tricky, okay? And I'm going to try to make it as black and white as I can make it. And I think I can make it pretty black and white. Okay. All right, so just a little bit of information. Okay. Okay, here's what's going to happen. Given f of x, really given the graph of f of x, given an original curve. Okay, you're going to be given the graph of f of x. You're not given the equation of the graph. Given f of x, or really the graph of, I should put the graph of f of x. Now come in here and graph f prime of x. Okay, let's see if I can sketch this. All right, I'm trying not to make this too messy. If I get too messy, I can just really blow this for you. All right, so suppose we have a curve that looks something like this, the original curve. I've already messed it up. Something like this. This is your original f of x. All right. So, the slope of the tangent line to the curve is your first derivative, your f prime of x. So let's think about this. We're going to get some ideas. Let's see. At x equaling 0, the slope of the tangent line equals what do you suppose? Here's the slope of here's the tangent line. What is the slope of this tangent line? 0. There you go. So the slope of the tangent line equals 0 when x is 0. Now, suppose x is 1 right here. And let's get this little tangent line going on. Okay. So, at x equaling 1, the slope of the tangent line looks like what? I'd say -1. Don't you think? It looks pretty darn close to -1. Right? So now let's look at an x value of 2 right here. And here's where we're going to get a little more kind of guess it. Okay, here's my tangent line at an x value of 2. And we're just going to really take a wild guess. How about a -3/2? And what I did was I kind of looked down here and up here, and I went up 3 and over 2 kind of thing. Okay, so now at 3, when x is 3, right here is your tangent line. Okay, and I'm going to say the slope of that one. What do we say? Negative 2/3. Okay, at x equaling 3, the slope of the tangent line looks like a negative 2/3. Okay, you can see how fun this is. Okay, at x equaling 4, the slope of the tangent line looks like what? 0 again. And let's do one more. At x equaling 5, the slope of the tangent line looks like it would be I'm going to say positive 1. What a mess. What a mess. What a mess. So this is your x-axis, and this is your y-axis. But in this case, our y is the same as f of x, right? Okay. So now what's going to happen is they're going to ask us to graph f prime of x. So now we're going to have these same x values, but the slope of the tangent line is our f prime of x. The slope of the tangent lines, because remember f prime of x is the limit of the difference quotient, which is going to give us the slope. So the slope of our tangent lines is what's creating our first derivative function. So to get the graph of the first derivative, these are my x values and these are my y values, which is the slope of the curve at these points. So this is f prime of x. So when x is 0, y is 0, which is f prime of x. That's supposed to be x is 1. Y'all change that. That's supposed to be x is 1. When x is 1, the slope of the tangent line is negative 1, right here, down 1. When x is 2, the slope of the tangent line is a negative 3/2, a negative 1.5 right here. When x is 3, the slope is a negative 2/3, back up here. When x is 4, the slope is back to 0. And when x is 5, the slope is 1. So the first derivative function, and this got kind of, it's not very hard, it's hard to see it. The original function looks like this. And the first derivative's graph looks like this. Pretty weird, right? This is your first derivative because we graphed it with the x values and the slope values of 0, 0, 1, negative 1, 2, negative 3/2, 3, negative 2/3, 4, 0, and 5, 1. That is the graph of the first derivative function. Now, what they ask you to do, and this is kind of difficult, is they show you stuff like this. And they say, here's your function. Which one of these is the first derivative graph to that function? See how we're going to do that? Here's f of x. Which of these is the first derivative graph to that function? You got to really be thinking about this. Okay, really be thinking about it. It's not an easy thing to make happen. So let me show you a little bit. Suppose this is what your graph looks like, and we'll do a little bit of an example of this. There is not a clock in this room. Whew, we're running out of time. Okay. Okay. So suppose your original f of x looks like this, which was right in that homework set that I just showed you. Okay, suppose this is f of x, and you're trying to match the graphs. Well, you look at this and you can say, okay, when x equals -2, what does it look like the slope of the tangent line is over here at -2? I don't know. It's kind of steep and it's going to be negative, right? So let's guess it at -5. Okay, at x equaling -1, right here, the slope of the tangent line is still negative. It's not as negative. We're going to kind of guess it. Maybe it's -2. At x equaling 0, what is the slope of the tangent line? 0. At x equaling 1, the slope of the tangent line is going to be just a reflection of the one over here at -1, so it's probably a +2, right? Because this is a parabola. It's going to have properties of being reflective over that y-axis. And if x equals 2, this slope of this tangent line should be comparable to the one at -2, so we'll call it +5. So now when you come down here to graph the first derivative, this is f of x, this is going to be f prime of x. Okay, when x is -2, your slope is -5. 1, 2, 3, 4, 5. When x is -1, your slope is -2. When x is 0, your slope is 0. When x is 1, your slope is 2. And when x is 2, your slope is 5. And look at what your first derivative function looks like. I don't think I graphed it just perfectly. Did I? Looks something like this, right? How can that be? That's pretty cool. Okay. So this was actually number 27. If this is f of x, this one's f prime of x. You see it? F of x, f prime of x. It's going to take y'all a little time to make that happen. That's not an easy process, but we're running out of time, and I will come back with our next lecture and pick up the next example. Hang on to the handout which I just gave you, and we'll go over it when I get a chance to finish this recording. Thank you guys for hanging in there to the end, and we'll see you on Wednesday.